All right, guys. So now that we're here and we're actually finally ready, so make me feel it like you guys actually want to be here. Okay? All right. Like you want to be here. Class.
Yes.
Thank you. Thank you. Appreciate it. I really do. Okay. Fake the funk until it's like a real thing. Anyway, continuity at any number. So for something to be continuous, what has to happen? Left side, right side, and the function, right? So right there in the middle, so the function also has to be equal at that point. So left side goes to the number, right side goes to the number, and the function goes to that same number. Analogy, roller coaster. Is it a roller coaster? Does the roller coaster track work? Yes. You don't want any holes in your track, you don't want any jumps. So for this to work out, this is actually a piecewise function. So all these things. So as x to the left side of x, to the right side of x, and x is. So let's see. When x is 3, this number is 9. Yes? Now, the left side has to also approach 9. So let's see how I do this. So if I'm starting with the left side here, as x is less than 3, let's go ahead and factor my numerator. Factor the numerator, I get x plus 3, x minus 3 over x minus 3. Those cancel. So that's why it does not equal right there, okay? So that's why it's a piecewise function, so it cannot equal to 3. But if I plug in 3, what do I get? I get 3. Do I get 9? Maybe the fan's too loud. I can't hear it. What'd you say?
For what question?
The one I just said. What do we get? 6? Okay. Yeah. That's gotta be the fan. I'm mostly deaf anyway, so too many blowing up of stuff in my 20s. Anyway, so this comes out to be 6. Automatically from here I could say that what? Not continuous, right? So if any one of those parts fail, it is not continuous. There we go. Está muy fácil? Sí, sí. Continuity at a number. Definition. Removable discontinuity. That's the holes that I've been addressing. Put this back on. Let f be a function that is defined everywhere in an open interval containing c, except possibly at c. The number c is called a removable discontinuity of f if the function is discontinuous at c but the limit exists. Discontinuity is removed by defining or redefining the value of f at c. That's what we did right there. Okay? It gives me a hole in my graph. By definition, it is a removable discontinuity. Next one. Graph the function of f is removable discontinuity. It has a hole here. Discontinuity is removable because we can fill in the hole by approximately defining f. The function will be then continuous at that. So, determining whether a function is continuous at a number. Now, this is a floor function. What does it look like though? What does it look like? It looks like what? This symbol right here, which is important. That symbol is a floor function. So does that look like absolute values? Yeah. It looks like absolute value, but if you notice, there is a foot right here. Ah, dang it. Right there. So there's a foot underneath it. So it's a little piece on the bottom. So that's a floor function. What do you think a ceiling function will look like? On top, right? The little thing on top. So I'm gonna go to my calculator. So I tried to do the install yesterday, and it did not work out because you have to have like special government clearance to be able to install any software, and my top secret clearance is not enough to install this program that I have on one of my computers, but not the other one. So I'm gonna go to, there we go. There we go. Go to my NumWorks calculator. And I'm gonna go to graph. You guys actually have it slightly differently. Okay. And this one right here, I'm gonna look in the toolboxes because I can't remember where this one's at. Nope, it's not there. Units and constants. Not there either. Let's try list. Operations. Not there. Alright, for you, it's in the toolbox. You guys could actually see it in the toolbox, but I can't bring that up right now because I don't know where it is on this one. Matrices and vectors. Nope, still no. Alright. I know there's a way I could search on this one. I did it before. You guys find the floor on yours? Can I see yours? Oh. Yeah, just floor. So, yeah, it just says type in floor. So it doesn't have a symbol on there. You just go to your graph and type in the word floor and then open parentheses. There we go. And if you notice it changed from the script to that, open parentheses. And then this is just going to be an X. Did you find it? Yeah, type in the word floor. There's templates. So I didn't have it anywhere in these templates. Function. Dang it. Alright, so apparently this one doesn't have it. I think I actually, did I put it in the graph for the next one? Actually, I did, dang. Okay, I'm pretty smart. So, as we plug it in at X, when you type in the word floor and just the letter X, okay, parentheses and X, did everyone get that one or no? Yes, Vincent, you get it? Okay. So floor function would be looking like this, and it just looks in the steps. So what's gonna happen is, if it is 1.1, it stays at 1. And it always go down to the next integer. 1.2, next one, still 1. 1.3, still 1. 1.4, still 1. 1.4, 1.9, still 1. And as it goes to 2, you notice right here, as it's going up, as it goes to 2, it goes up to the next number. So that's what a floor function is. It's always going to be the lowest, or rounding down everything to the integer. That's what a floor function is. So it's always going to be these steps like this. So if you notice, once it actually gets to the number 2, it is no longer right here because it is approaching that number. But once we get to 2, it is a solid dot here because that's when it's at the next number. So the left side approaches this, or the right side goes at this. So is it continuous at the number 1? You said no? Okay, for it to be continuous, left side, right side, and the function all have to go to the same number, right? So this being a floor function, that's what happens. So this one is discontinuous. Would I want to be on a roller coaster that looks like this? No. This looks closer to Mario climbing up the stairs at the end, right? So, alrighty. Okay, definition, one-sided continuity at a number. Now this time we're just going to look at it from one side. Let f be a function defined at the interval parentheses, which means open, a, comma, c, bracket, which means closed. That's important. So is it equal to a? Say no. No, parentheses means not equal to. Bracket means equal to. So in that interval, or that notation, parentheses means not equal to, bracket means equal to. It's like open dot and close dot. Continuous from the left at number C if the left side is equal to the function. So it doesn't matter about the right side. Let f be a function defined on the interval bracket C, comma B, parentheses, and is continuous from the right at a number C if the right side is equal to the function. Now I'm going to go back to the previous right here. This is an example of the right side is equal to the function. So I could say that this is continuous on the right side, but not the left. So that's the one-sided continuity. I cannot say that this is continuous from the left side, because from the left side this goes this way, but it's not equal to the function which is up here. Does that make sense? Tree, you good? Okay. Now, function is continuous on an open interval. This is important. So now, if you notice there's a little star right here on your notes, this is important. It is continuous on an open interval. So, parentheses, a, comma, b, parentheses, continuous at every number in there. There is no undefined in between there. But does it have to be equal to the endpoints? Why no? I'm not just throwing up gang signs here. The parentheses means it does not have to be equal to at the endpoints. It has to approach it, but not be equal to. Okay, that's important for this one right here. A function is continuous on an open interval. I'm sorry, continuous on an interval a to b if it's continuous on the open interval a, b, and continuous from the right at a number. So this is right side here, so this is closed. So this is important about the interval from here to here. it's gotta be equal to on this side. Continuous on interval, this is gonna be equal to on the right side, is continuous on everything here and at B, so it has to have a closed dot at B. The function is continuous on a closed interval. Now this is important, everything else is just intervals. This is closed, this one is open. A closed interval means that A, closed dot, B, closed dot, and there is no undefined places or things that does not exist or holes in between A and B. So it's going to be continuous on the open interval, and it also must include A and B. Does that make sense? Okay, so I'm going to write what this is going to look like as a set notation or interval notation. So this as an interval notation would be an open dot at A, open dot at B, and it is everywhere in between. On interval notation here, this would be a closed dot at A, and it is a closed dot at B. Are you guys okay? Interval notation. Have you guys done interval notation? Or seen this before at least? No? Because I'm assuming a lot, because I this used to be like the standard, like back in the day. And so, but some people are looking at me shaking their head, so I'm getting worried. So this is again me assuming. You've never seen this before. You have? I can almost understand what you're saying. Is that a yes? Yes.
We seen it in AP pre-code.
Last year, right? You guys did some of this last year? Or you don't remember it?
I was in a different school the first
Oh,
semester.
hey, no worries. Okay, so what again? If you're questioning something, speak up, because there's something that you're looking at, and quite often it happens in classes like this because not everyone had the same introductory classes, or what, like the class that preceded this. You might have had a super sucky teacher that gave you an A because you brought him candy every day. We have a teacher like that. I'm not going to tell you who it is. People are going to be listening to this, be like, who can I get an A from just to get a, yeah. Anyway, but still, so interval notation. So if I think about this as a number line, 0, 1, 2, 3. On a number line, I would say open dot here, and let's say close dot here. And as a notation, looking like this would be my parentheses, 0, comma, 3, bracket.
I did go over that minus card.
Okay, so yeah, but these right here, for these, with the line graph and stuff, yeah, stuff like that. So if you see it like that, then that's what it means in between the different things. Good now? Okay. So again, if there is something you don't understand, speak up, because guess what? This is a small group. You're not in college right now. Well, technically you are going to be. You're not in college right now, but this is a dual enrollment class. Anyway, in college classes, there's like 100 or more in your introductory math classes. In your lower level math classes, you get a whole bunch of people. They just cram them all in there. No one ever really gets a chance to ask any questions. It's more of a lecture than a teaching. So they just talk about whatever and expect you to do all the work. So, but ask, speak, okay? I want this closer to be a, I don't know, like a study group type thing versus, me preaching. Alright, so here's the examples for this. This is going to be my graph, and this one right here, I don't know if you guys can see this. This is A, comma, B. This one right here is A, comma, B. Both sides open. This next side is A, comma, B. Next one is B, and this one is bracket A, comma, B. Now, the difference on this one and this one, it is defined at this point here, but it's not part of my interval. Same thing goes for here. It is defined here, but not on my interval. So it's not on my line. Alright, I'm gonna leave off on this, if you could please. And from here, I asked you guys to bring up your MCID thingy, right? Remember when I talked about the AWC, or not, the PC stuff. I teach for AWC also. Okay, so the PC stuff. So, did you guys have that information available or no? Okay, have you done any dual enrollment before? Nope, guess what? You get to actually do that right now. So, I'm gonna leave off here. We're gonna use this for some more homework, and then we're gonna pick up the more difficult concept Monday. So that I wanna have plenty of time for this. So we'll pick up that on Monday. So like, share, and subscribe, hit that notification button, support my channel.